Hi guys, and welcome to this virtual lecture course on Quantum Condensed Matter Physics. I'm Dr. Andrew Mitchell, and in this lecture course we'll be considering the quantum mechanics of many particle systems. In the first part, we'll be considering spin systems and using them to describe magnetism in real materials. But to be able to do that, we need to understand the formalism and the basics for simple spin systems. This is described in terms of the so-called second quantization formalism. This involves raising and lowering operators for the intrinsic spin angular momentum. To be able to do this, we will study in this lecture exactly how to set up these kind of problems. We will actually start by re-examining the quantum harmonic oscillator, a problem I'm sure you're familiar with by now, but we'll be looking at it again with a perspective towards second quantization. We'll be looking closely at the raising and lowering operators for the quantum harmonic oscillator and interpreting them in terms of creation and destruction operators for bosons. We'll then look at the raising and lowering operators for orbital angular momentum before generalizing this to the intrinsic spin angular momentum of electrons. In the end of this lecture, we'll consider a single spin half particle, an electron. We'll look at the operator algebra, the symmetry, the kinds of Hamiltonians you can write down for such a system, and we'll study basically everything that one can do with a single particle. In the next lecture, we'll generalize the framework to two particles. This will allow us already to expand upon everything that we've done so far and allow us to treat a wider range of problems, but it'll also point the way to treating truly many particle systems. In real materials, of course, we have 10 to the 23 particles, so that's a big step up. We need to develop the formalism rigorously, and that's what we'll be doing in this lecture. So let's get down to work.
In condensed matter physics, we have to deal with systems with many interacting quantum particles. The language we use to describe such systems is called second quantization, and involves so-called creation and annihilation operators. Trying to solve complex quantum systems without the use of second quantization quickly becomes very, very difficult and cumbersome. This language of second quantization really makes things a lot easier, and in many cases allows us to really solve problems that couldn't be solved any other way. In fact, you will have come across creation and annihilation operators previously in introductory quantum mechanics in relation to the study of the quantum harmonic oscillator. So in the first part of this lecture, I will actually recap the physics of the quantum harmonic oscillator using this second quantized notation. And in the second part of the lecture, we're actually going to use the second quantized form of the spin operators to describe electron spin in real systems. So in this recap of the quantum harmonic oscillator, we'll see how we go from the usual language of quantum mechanics involving position and momentum operators, so-called first quantization, to the language of creation and annihilation operators, which is called second quantization. This is fairly standard stuff. You can see it in many of the standard textbooks, but here I'll try to emphasize a particular perspective that will be useful to us in this course. The first task is to write down the Hamiltonian for this quantum system, H, and I will denote operators for now with this hat on the top. And the Hamiltonian consists of two terms. There is a kinetic term, which can be written as p squared over 2m. Here, p hat is the momentum operator for the particle and m is the particle mass. And then to this kinetic term, we add a potential term, which is basically a quantum version of Hooke's law, a potential half kx squared, but again here x has a hat on it, denoting the fact that it's an operator. As usual, the momentum operator p hat is h bar upon I of d by dx. And therefore, we can compute the commutator of our operators x and p. This just means operator x times operator p minus operator p times operator x. And we see that in quantum mechanics, unlike in classical mechanics, this commutator is finite and doesn't vanish, and it gives the value I h bar. These are the canonical commutation relations of quantum mechanics. We call these canonical commutation relations because the position x and momentum p are canonical variables. They are conjugate to one another. Now, it's often convenient to introduce a parameter omega, which is simply the square root of k over m, such that our Hamiltonian be written in this slightly simplified form 1 over 2m into p hat squared plus m omega x hat squared. We can now write down the Schrödinger equation. Here I'll just use the time-independent Schrödinger equation to get the static quantities. We say that the Hamiltonian acting upon a wave function psi I gives us the wave function psi I back again times the corresponding energy EI. This is an eigenvector equation. The wave function psi I here is the eigenvector, and the energy is the corresponding eigenvalue. We can now plug the Hamiltonian into this Schrödinger equation to obtain the following. This is then an equation we can solve to obtain our wave functions and energies. So how do we go about solving this kind of equation? To solve this Schrödinger equation, we will actually introduce new operators a plus and a minus. They are defined as follows. We define the operator a plus as m omega x minus ip. And there's some normalization constant I will talk about later, 1 over root n. The corresponding a minus operator is defined as m omega x plus ip, again with the same normalization factor, 1 over root n. So this might seem a bit counterintuitive because a plus goes to the minus sign here and a minus goes to the plus sign here, but we'll see why this is a natural definition in just a moment. So with these definitions, let's now compute the commutator a minus with a plus. Remember the definition of quantum mechanical commutators. This simply means a minus a plus minus a plus a minus. So let's now just calculate each of these two terms in turn. So we just use the definitions here to expand out this product, and we have to just be careful about the order of these operators. A minus comes on the left, a plus comes on the right. We have to be careful because we know that the canonical operators x and p themselves do not commute. As always with quantum mechanics, we need to be very careful with the order of operators. So when we're careful doing that, we obtain the following. We get one piece m omega x squared, one piece plus p squared. Here, notice we've got ip times minus ip gives us plus p squared. And then we have the cross terms, again, just being careful with the order of these operators. Now, importantly, this term here is the definition of the commutator x, p that we talked about earlier, and we know that has the value I, h bar. So therefore, the product a minus a plus gives us 1 over n into m omega x squared plus p squared plus m omega h bar. Very similarly, if we form the product a plus a minus, we get exactly the same thing, except the plus m omega h bar turns into a minus m omega h bar. Maybe you can already see why that is. It's because we swap the order of these two terms here, and therefore we swap the order of this commutator, turning it from a plus into a minus. I will leave that as an exercise for you to confirm. We can then very simply form the commutator a minus with a plus. It simply gives us 2m omega h bar over the normalization n. This is nice because all of the operators in here involving x and p have cancelled out, just leaving us with this pure constant. Furthermore, we can actually set this constant to 1 by a proper choice of our normalization constant n. Obviously n is therefore simply 1 over 2m omega h bar. And this is the definition of the normalization constant n appearing in our original expressions for the operators a plus and a minus that we'll use in the following. With this definition, we can actually write A minus A plus in a slightly more simple form. We can write it as 1 over h bar omega times the original Hamiltonian h plus 1/2, whilst the combination A plus A minus can be written as 1 over h bar omega times the Hamiltonian h minus 1/2. This is nice, and it allows us to express the Hamiltonian itself, h, in terms of these new operators. We can write h as h bar omega into A plus A minus plus 1/2, or we can express it slightly differently using the other expression as h bar omega A minus A plus minus 1/2. Both of these expressions are equivalent and are different ways of writing our original Hamiltonian in terms of these new operators. Okay, so what's the point of all of this, and how does it help us solve the Schrödinger equation? So we have our expression for the Hamiltonian written out here again in terms of these new operators. So let's now suppose that the function psi is a solution of the Schrödinger equation with an associated energy E. What I mean by this, of course, is that I may write h times psi is equal to E times psi. Let's now consider a new function phi, which is obtained by acting on our wave function psi with the operator A+. What happens when we act on this function with the Hamiltonian? Well, of course, we can unpack this and write it as h acting on the operator A+, acting on the wave function psi. Let's now write the Hamiltonian using this first definition here. We can write that as h bar omega into A plus A minus plus 1/2, and then we multiply this by A plus and psi. This is an interesting expression because I can actually factorize out a factor of A plus acting on the left-hand side. Namely, I can write this in the following way. H bar omega here is simply a constant, and therefore we can commute it through this operator A+. Using now the second definition of our Hamiltonian involving the operator A minus A+, we can then rewrite the second term in this way. We therefore see that we can act on the wave function psi with h bar omega, just a constant, and also the Hamiltonian. According to the original Schrödinger equation, h psi is equal to E psi. We note that h acting on psi therefore gives us simply the energy, and so we may write this. Everything inside the brackets is simply a constant. It's the energy plus h bar omega, it's just a number, and therefore, again, we can commute this operator A plus through that constant and obtain E plus h bar omega multiplied by the operator A plus acting on psi. But of course, A plus acting on psi is exactly our original definition of the function phi. And so, I may write this as E plus h bar omega times phi. What we've seen, therefore, is that when h acts upon phi, we get phi back again with an associated eigenvalue E plus h bar omega. This is an extremely important equation. It tells us that if the function psi satisfies the Schrödinger equation with an energy E, then the function phi also satisfies the Schrödinger equation with an energy E plus h bar omega. That's what we see down here. This equation is an eigenvector equation where phi is the eigenvector of h, and its associated eigenvalue is no longer E, but now e plus h bar omega. What we've proved is that if we have a single eigenfunction psi, which satisfies the Schrödinger equation, then we can generate a new eigenfunction phi, which also satisfies the Schrödinger equation. If psi has an energy E, then phi has an energy E plus h bar omega. This equation here is an eigenvector equation, just like the one we started with. Furthermore, there's some inductive reasoning here. Once we've obtained phi, we can generate a new function by acting upon that with a plus. I will leave it as an exercise for you to check that if we apply the operator a minus to our wave function psi, we also get an eigenfunction. What I mean here is consider a function beta, let's say, which is obtained by acting with a minus upon our original wave function psi. We can then write our Hamiltonian acting upon our function beta, which is of course equivalent to the Hamiltonian acting upon a minus acting on psi, and just go through the same process as before. What you'll find is that the Hamiltonian acting on this function beta gives you back the same function beta with an eigenenergy E, this time minus h bar omega. So, if we act on a wave function psi with either a plus or a minus, we generate a new eigenfunction. The corresponding eigenvalues are either increased in energy by plus h bar omega if we use the a plus operator, or they're decreased in energy by minus h bar omega if we use the a minus operator. That is why we call these things ladder operators, because we move up in a ladder of energies, starting from E, and then E plus h bar omega, E plus 2 h bar omega, and so on. That's if we use the a plus operator. We can call this a raising operator. On the other hand, if we use a minus, which we can call a lowering operator, then we start off from energy E and then progressively reduce the energy by h bar omega each time we act with a minus. Raising operators therefore increase the energy, and lowering operators therefore decrease the energy. If we have a given eigenstate, we can generate new ones in a ladder starting from that state using these a plus and minus ladder operators. But the energy of the quantum harmonic oscillator cannot be negative. Remember, the Hamiltonian in its original form was the sum of two squares, p squared plus x squared, so this object cannot be negative, and h, of course, is giving us the total energy of the system. What that means is that if we have a given eigenstate of the system psi, and we apply the lowering operator, we cannot do this indefinitely, because eventually the energy here would become negative, and we know that there is no negative energies of this system. Therefore, there must be a minimum energy. So, we'll denote the eigenstate with the minimum energy E naught as psi naught. This will be our ground state. We cannot act on this state with the lowering operator because it would give us a negative energy, so this is really the lowest energy state of our system. That means that if we act on psi naught with a minus, we would get 0. No state with a lower energy than psi naught exists by construction. If we now substitute in our definition of the operator a minus into this expression, we obtain the following. Furthermore, I can use the definition of p hat to be h bar upon I d by dx, and obtain the following differential equation. This differential equation can in principle be solved to obtain the ground state wave function psi naught as a function of x. Indeed, we can fix the constants of integration that arise by using the normalization condition for the wave function. When we do that, we get the following for the ground state wave function. Importantly, we see that it has a Gaussian distribution. We have an e to the minus x squared featuring here. Furthermore, if we plug this function into our Schrödinger equation, we indeed see that it is an eigenstate of the Hamiltonian with an associated energy E naught given by a half h bar omega. This value E naught is called the 0-point energy. This is consistent because if we were to try to operate on our psi naught ground state wave function with the operator a minus, that would lower the energy by 1 quanta h bar omega, And we'd see that that would take this into a negative value. And the ansatz that we started with is that the energy of the quantum harmonic oscillator cannot be negative. So indeed, this is the ground state. We can now construct all of the other eigenstates of the system. For example, we can define psi1 as being A plus acting on our ground state psi naught. We know that psi1 would satisfy the Schrödinger equation. That means that H acting on psi1 gives us E1 times psi1 with an associated eigenenergy E1, which is raised with respect to E0. So E1 is equal to E0 plus h bar omega, and given that we know that E0 is the ground state energy, half h bar omega, overall E1 gives us 3/2 h bar omega. And in exactly the same way, we can generate all of the eigenstates in the system, which will produce a ladder of energies starting from a half h bar omega and then going up in integer units of h bar omega. Of course, we can also use the operator identity for A plus to act upon our ground state wave function written here to generate the exact form of all of the other wave functions. However, the beauty of this second quantization formalism that I'm describing here is that you actually don't need to work explicitly with these complicated functions. We can just work with these objects psi0, psi1, and so on, and understand the relationship between them in terms of these raising and lowering operators. So we can generate a ladder of eigenstates satisfying the Schrödinger equation H psi n is equal to En psi n, and we start from the ground state psi0 with corresponding ground state energy E0 equals a half h bar omega. We can then generate the new eigenstates simply by acting on a given eigenstate with the A plus or A minus operators. This generates us a ladder. We showed that when we act on a given wave function, let's call it psi n, with A plus, we generate a new eigenstate. We also showed that when we take a given eigenstate psi n and act on it with A minus, we get an eigenstate back. In fact, all we showed actually is that the things that we generated are proportional to eigenstates. They satisfy the Schrödinger equation, but also, of course, the eigenstates need to be normalized. And if we do this properly, we actually see that we get a normalization factor square root n plus 1 here for the raising operator and a factor of square root n for the lowering operator. That's basically just a small detail. It arises from the normalization condition. Furthermore, we can obtain our eigenenergies recursively. We can say that En plus 1 is related to En by adding on h bar omega. Again, this holds for all n greater than or equal to 0. And En minus 1 is equal, therefore, to En minus h bar omega, again obtained by acting on our eigenstates with the A plus or A minus operators. These are, of course, recursive equations that relate psi n to psi n plus or minus 1 and En to En plus or minus 1. But of course, we can close these equations and write down in closed form the expression for a given psi n and a given En in terms of the ground state wave function psi naught and the ground state energy E0. We see that the wave function psi n is just obtained by acting on the ground state wave function psi naught with the A plus operator n times. Likewise, the energy En is obtained from the ground state energy half h bar omega by adding n lots of h bar omega to it to obtain this expression. In particular, notice that we have quantized energies. In the quantum harmonic oscillator, the oscillator can only take certain energies that are determined by this quantum number n. The energy gaps between neighbouring eigenstates is exactly an integer of h bar omega. H bar omega is therefore the quanta of energy in this system. So let's use this machinery to now discuss the so-called occupation number formalism and the Dirac bracket notation. First of all, let's define a number operator n hat, which is given by the product of our A operators, A plus, A minus. Why do I call this a number operator, and what effect does it have when I apply it to our wave function psi n? So, first of all, let's apply the operator n hat to a given wave function psi n, that means A plus, A minus acting on psi n. But here we know how A minus acts on psi n. We get root n times A plus acting on psi n minus 1. Then we can act again on psi n minus 1 with our operator A plus, and we get n times psi n back again. So this is interesting because we see that a given wave function psi n is an eigenvector of the operator n hat. So we're not talking about eigenvectors of the Hamiltonian now, we're talking about eigenvectors of a different operator, this number operator n hat. So when n hat acts upon psi n, we get psi n back again, that's the characteristic of an eigenvector equation, with an eigenvalue of n. So to summarize, psi n is an eigenfunction of n hat with the eigenvalue n. Furthermore, n hat commutes with the Hamiltonian h. What I mean by this is that if we form the commutator n with h, which of course just means n h minus h n, then this object is actually equal to 0. Using the definitions that we've already established, this is very easy to show. I'll leave that up to you as an exercise. What does it mean then if n commutes with h? If two operators commute, it means that we can form a simultaneous eigenbasis. What this means in the present context is that our wave functions psi n are simultaneously eigenstates of n as well as h. This tells us that n is a good quantum number. We can label our states psi according to this quantum number n. In fact, I've already implicitly been doing this by calling the psi n's by this label n. We now see what this n actually means. It's a quantum number, and it's the eigenvalue of the operator n hat. In fact, this is very general. If we have an operator that commutes with the Hamiltonian, then it means that that object is actually conserved, and therefore this serves as a good quantum number. Using the Dirac bracket notation, we can write that eigenvectors of h are labelled by this ket here with the quantum number n. We can then write down the Schrödinger equation in this nice compact form. The ket n stands for some complicated function in this case, but we don't actually need to deal with those directly. We can just use these symbolic representations using the Dirac bracket, labelled here by the quantum number n. We also know that these kets are eigenstates of our number operator. So I can write down an eigenvector equation that looks like this. Indeed, let's remind ourselves that in our original notation, we wrote down the Hamiltonian h as h bar omega into a plus a minus plus 1/2. Now we recognise, of course, that the object a plus a minus is the number operator n hat, and so I can actually write down the Hamiltonian as h bar omega into n hat plus 1/2. The corresponding energies are obviously then trivial. En are simply h bar omega into n plus 1/2, where n here is the quantum number, not the operator. So in the Hamiltonian, we have n hat. In the eigenvalue, we have n without the hat. In terms of the number operator, this problem becomes very simple indeed. I have a bunch of eigenstates labelled by the kets n. The lowest state, 0 ket, is the so-called vacuum state with no particles, and then as we act with a+, we can put more and more particles in to generate the 1 ket, the 2 ket, and so on. And we can simply read off their energy according to this equation. It's become very simple because we're labelling our states according to a quantum number, and the Hamiltonian depends in a simple way on that quantum number. Later on, we'll see some more complicated systems which can nevertheless be cast in a similar form to this. So this is a rather instructive example. So let's go through some of the algebra. If I act on the vacuum state 0 with a+, I generate the state 1. On the other hand, if I try to act on a- onto the state 0, I get 0. Not the state 0, but literally just nothing. That's because we annihilate this vacuum state. We can't take any particles out of this state because it's already empty. That's what we mean by the vacuum state. We saw earlier that we can't have an energy that's lower than the 0 state. And this corresponding energy, a half h bar omega, is the 0-point energy of the system. Likewise, I can act with A plus on the 1 state to generate the 2 state. Don't forget there's this normalization factor here given by square root 2. And I can act with a lowering operator on the 1 state to regenerate our ground state 0. And thereby we can assemble our whole ladder of states, starting from the ground state 0. A plus is therefore viewed as a creation operator, while A minus is viewed as an annihilation operator. This refers to adding or taking out particles from this so-called vacuum state. The vacuum state has no particles. What are these particles, you might ask? Well, they're actually bosons, and we know that because A plus and A minus have the bosonic commutation relation. This is an important relation, and we explicitly established this operator algebra earlier on. Importantly, this is the commutator that corresponds to canonical bosons. So if I have a lowest state, that must be the vacuum state, and every time I use A+, I'm adding a particle, and those particles must be bosons. We'll talk more about this later. For now, let's carry on with our recap of the Dirac bracket notation for this problem. If I have a given state described by n, then I can take the dagger of this, that means the adjoint or the conjugate transpose, and this will give the corresponding bra n. Our states form an orthonormal basis. Therefore, if we take the inner product of n with m, what I mean here is we're making this matrix element of n bra with m ket, then we get the Kronecker delta. This object here, of course, is just a mathematical shorthand, which means it's 1 if n is equal to m, or 0 if n is not equal to m. What that means physically here is that if I have a given state n, then it is normalized to 1. If I take the inner product with itself, I get 1. That's basically equivalent to integrating over all space. On the other hand, if I take different functions, n and m, then they are orthogonal to each other. If I multiply one function by the complex transpose of another and integrate over all space, then I'll get 0. So together, this neatly encapsulates both concepts of orthogonality between different states and normality of a given state. The kets n also form a complete basis. What this means is that I can resolve the identity. I can write an operator 1 hat, which is meant to indicate the identity. This is the sum over all states of the system n, which in this case are all of the kets starting from n equals 0 all the way up to n equals infinity. And we have this slightly weird object here, which is an operator. It's a projector. It takes us from a state n and returns us back into a state n. Now, we know that this is equivalent to multiplying by 1, because if I take this operator 1 hat and I apply it to a given ket m, then I get the sum over n of this object, which is the identity as I've just defined, and then I have the ket m operated on here. Now, from this orthonormality condition here, we see that from this sum, all of the terms are 0 except when n is equal to m, and therefore overall, this whole thing is just equal to m. And that's true of any ket m. What we've proved there is if we operate on any ket m with our identity operator 1 hat, we get the same state back again. So that's why it's like the identity. It's like multiplying by 1. We don't really do anything. However, this confirms that we have a complete basis because we return our ket m for any choice of our m in here. This tells us that our identity operator spans the entire basis. Together, these properties of orthonormality and completeness establish this as a good basis for our quantum mechanics. This basically concludes our recap of the quantum harmonic oscillator and the introduction to these creation and annihilation operators. What I now want to do is turn to the case of electron spin, and we'll do that by starting off with the angular momentum algebra. We will then talk about eigenstates and raising and lowering operators for electron spin. In the future lectures, we'll then use this algebra and this formalism of second quantization to actually look at some spin models and solve those models. This will help us understand the quantum foundations of magnetism in materials. So now I want to discuss the quantum mechanical operators for angular momentum, and with these at hand, we'll then be able to directly construct the operators for electron spin. This first part is again rather straightforward and can be found in any introductory quantum mechanics textbook. First of all, note that in the classical world, the angular momentum L is given by r cross p, and therefore in component form we can write, for example, the x component, Lx, is equal to y pz minus z py. The form of this just follows from the vector cross product r cross p. The quantum mechanical counterparts share the same relationship, except that here, of course, we have momentum operators p hat, which are related to the spatial derivatives. So we have a quantum mechanical angular momentum operator around the x-axis, Lx hat, which is simply given by y hat pz hat minus z hat py hat. All of these are quantum mechanical operators. Now, importantly, and unlike in the classical world, these operators for position and momentum do not commute with each other. And that means that the components of angular momentum likewise do not commute. The properties of angular momentum in quantum mechanics are characterized by the commutation relations between the angular momentum operators. So let's calculate them. If we calculate the commutator of Lx with Ly in the quantum mechanical world, we see that this is not zero. It gives us I h bar Lz hat. I will leave it as an exercise for you to check this one explicitly. Indeed, the other commutators of the angular momentum operators are obtained from this one through their cyclic permutations. What I mean by that is, instead of Lx with Ly, if I were to consider Ly with Lz, I would be able to write down that this is I h bar Lx. Finally, I can write down that Lz with Lx is equal to I h bar Ly. I can write these down right away through this cyclic permutation property because I see that x, y, and z appear in order, in that order. So I see in here Lx, Ly, Lz. And then I have this wraparound property. That's what we mean by cyclic. So here we have Ly, Lz, and then we start again at Lx. Lz, then we start again, Lx, Ly, and so on. So the important thing to note about these commutators is that they're not zero. What that means is that we cannot form a simultaneous eigenbasis of the angular momentum along, for example, the x and y axes. To be able to form a simultaneous eigenbasis, we need to have the commutator of the two operators vanish. What that means is that we cannot write down quantum numbers corresponding to momentum along the x and y direction simultaneously. Now we can define a vector operator, L vector hat, which is simply a three-dimensional vector as usual, but in the x, y, and z components we have operators Lx hat, Ly hat, and Lz hat. If we now consider the square of this object, L vector hat squared, what we mean by that is we're taking the dot product of L vector hat with itself, L dot L, which then gives us a scalar quantity, Lx hat squared plus Ly hat squared plus Lz hat squared. And we can use these definitions to work out what that is in terms of the position and momentum operators. With that done, we can compute the commutator of L squared with Lz, and we'd find that indeed this was equal to 0. This is important because it tells us that we can label states by both the eigenvalues of L squared as well as the eigenvalues of Lz. We can therefore generate a good quantum mechanical basis for our system using states labelled by L and Lz. In fact, there's nothing special about the z direction. If we were to compute the commutator of L squared with Lx or with Ly, we'd also find they were equal to 0. However, this doesn't mean that we can specify L as well as x, y, z, because Lx, Ly, and Lz do not commute, as we already showed up here. It's traditional to label states by the total angular momentum L as well as the z projection Lz, rather than looking at the x and y components. So in this course, we'll stick with that convention. We will therefore define quantum mechanical states with definite angular momentum L and angular momentum z projection m as being this Dirac ket L, m. From the definitions I've written down, one can then show that the operator L squared acting on this state Lm gives you h bar squared L into L plus 1 times the state back again. The derivation of this is fairly standard. I won't get into it here. You can read it in any of the standard Introduction to Quantum Mechanics textbooks. Likewise, we can operate on our state Lm with our Lz operator. And in this case, we find that we get h times m, and the state back again, Lm. So the ket Lm is a simultaneous eigenstate of the L squared and Lz operators. L and m are therefore good quantum numbers. Just remember, however, that the eigenvalue of L squared is actually L into L plus 1, whereas the eigenvalue of Lz is m. Now, as with the quantum harmonic oscillator, we can define raising and lowering operators for angular momentum. It can be shown that a good choice is L plus is equal to Lx plus I-Ly, whereas L minus is given by Lx minus I-Ly. Since the total L squared commutes with the individual components Lx, Ly, and Lz, it's easy to see that L squared does commute with L plus and L minus. So what is the effect of applying L plus and L minus to a given state Lm? Again, to check this, you have to go back to the original definitions and then apply them to the chosen eigenstate. The philosophy here is very similar to that of the quantum harmonic oscillator. More details can be found in any standard textbook. We find that when we apply L plus to a state Lm, we obtain a new state Lm plus 1. Likewise, when we apply L minus to the state Lm, we get a new state Lm minus 1. This is why these things are referred to as raising and lowering operators, because we can see that we create a ladder of the z projections of the angular momentum, and as we apply L plus and minus, we go up and down this ladder. M increases to m plus 1 when we apply L plus, and m decreases to m minus 1 when we use L minus. The proportionality constant A-Lm, which connects these two, has a special form, and it's given by h bar multiplied by the square root of L into L plus 1 minus m into m plus or minus 1. So it depends here whether we're using L plus or L minus, whether we take the plus or minus in this expression. The form of this is very important because we'll see that for certain values of L and m, the coefficient A-Lm goes to 0. That means that for certain states, we cannot further increase the m or further decrease the m. In particular, analysis of this equation tells us that A-Lm is equal to 0 when L plus is applied to a state with m equals L, whereas A-Lm is equal to 0 when L minus is applied to a state with m is equal to minus L. This basically defines for us the maximum z component of the angular momentum as being m equals L, and the minimum z projection of the angular momentum m being minus L. So for a given total angular momentum L, we see that the maximum z projection is plus L and the minimum z projection is minus L. Why is that? Because if we take this expression here and we try to further increase the m value by applying L plus, then we'll see that if we're already at m is equal to L, then this will just give us 0 on the right-hand side. 0 on the right-hand side means there's no such state. We cannot further increase the z projection of the angular momentum. The maximum possible m is therefore L. Likewise, if we were to apply L minus to a state with z projection of the angular momentum m is equal to minus L, then we'd see from this condition that again this coefficient would vanish and the right-hand side would be equal to 0. There is no state with a z projection of the angular momentum that's lower than minus L. And since when we apply L plus or minus, the m changes by an integer, we can see that we have a range, a discrete quantized range of z projections for the angular momentum. We see that m can take values of from minus L to plus L in these integer steps. So in total, there are 2L plus 1 values that the z projection can take. As an example, let's consider the situation with total angular momentum L equals 2. This means that we can have z projections minus 2, minus 1, 0, 1, and 2. 5 values in total, 2L plus 1. We can depict that in the following way. We see the components of the total angular momentum along the x, y, and z directions here. This is Lx, this is Ly, and this is Lz. Now, we can draw a sphere centered on the origin of this coordinate system, and the radius of this sphere should be the total angular momentum, which in this case is L equals 2. So what that means is that I can draw an arrow from the origin to a point on the sphere. Let's say it's this arrow here, and the length of that arrow is L equals 2, the total angular momentum. We can make a projection onto the x, y, and z axes. In particular, the projection onto the z-axis is this one that we see here. In the case illustrated, we have m equals plus 2. Now, because we cannot specify simultaneously the x, y, and z components of the angular momentum, all we can say is that we have a z component of m equals 2 and is somewhere on this circle here. If we would have a different value of m, for example m equals 1, then we'd be able to say it was somewhere on this circle here. These circles are sections of our sphere of radius L. So let's say that we consider the specific state with L equals 2 and m equals 2. Well, if we apply the operator L squared, we get h bar squared times L into L plus 1, which in this case would give us 6 h bar squared times the state 2, 2 back again. If we were to apply the operator Lz to our state 2, 2, we get h bar times m times the state back again, which in this case is 2 h bar times the state 2, 2. If I try to raise the z projection of the angular momentum by using the L plus operator on our state, then because of the special form, as discussed on the previous slide, we see that this annihilates the state 2, 2 and gives us 0. There is no such state with an m value that's greater than 2 when we have L equals 2. Finally, let's consider the case of applying the lowering operator L minus to our state Lm, in this case the 2, 2 state. Here we have a slightly different form of this coefficient, as discussed on the previous slide, and indeed this one does not vanish. We see that it gives us a state 2, 1. The value of m is reduced from 2 to 1, and the coefficient here is 2 h bar. Altogether, this defines the operator algebra for angular momentum, and in practice, this is the kind of thing we would use to describe the orbital angular momentum of electrons in atoms. Of course, electrons also have an intrinsic angular momentum, which is called spin, and that's what I want to talk about next. Electrons are fermions and have an intrinsic spin angular momentum. In general, fermions have half-odd integer spin, and in the case of electrons, this is a spin s equals a half. In this course on quantum condensed matter physics, we'll be particularly interested in electrons moving around in solids, and therefore we need to take account of the electron spin. Indeed, we'll need a generalized framework for dealing with the spin of many interacting quantum particles. And this is where the second quantization formulation of spin angular momentum will come in particularly useful. In particular, we have exactly the same operator algebra for spin as we do for regular orbital angular momentum. As we saw, angular momentum is a vector operator, L vector hat, and for spin we have a corresponding spin operator, which is also a vector, S vector hat. We have three components, Sx, Sy, and Sz, which are operators. The components Sx, Sy, and Sz have the usual commutation relations for angular momentum. In this case, Sx with Sy gives IH bar Sz, and cyclic permutations thereof. We also have that S squared commutes with the Z projection Sz. This is important because it means they form a simultaneous eigenbasis, and we can label states by both their spin and their Z projection. In the case of electrons, we know that the spin is S equals a half, and the Z projection, Sz, can be plus or minus a half. We can again introduce spin raising and lowering operators as combinations of Sx and Sy. S plus is defined as Sx plus Isy. S minus is defined as Sx minus Isy. If we consider a single electron, S equals a half, and Sz plus or minus a half, then we have a two-dimensional Hilbert space. This is the full state space spanning all possible configurations. Since we showed that we can label our states according to S and Sz, here I'm writing down two Dirac kets, both of them S equals a half, but one of them is Sz plus a half, the other is Sz minus a half. This is actually the complete vector space for this problem, because we only have two states. It's conventional to describe these in terms of an upspin or a downspin. This refers to the Z projection of the spin, either plus or minus a half. Notice that these are basis states. They're not necessarily eigenstates of any Hamiltonian. We haven't mentioned any Hamiltonian yet. So far, we're just discussing the complex vector space relevant to describing a single spin-half particle. This basis is orthonormal because if we consider the inner product of a state with Sz and another state with Sz primed, then we see this is equal to the delta function of Sz primed. Put another way, it means that we can write the inner product of up with up is equal to 1. The inner product of down with down is equal to 1. This is because the up or the down spin wave functions are of course normalized. But if we take the inner product of up with down, these are orthogonal, so we get 0, and likewise down with up, we get 0. The basis is also complete, meaning that we can write, as before, an identity operator, which in this case is given by 1 hat is equal to a projector onto the up spin state plus a projector onto the down spin state. This has been designed so that if we apply our identity operator I onto any given state in the system, denoted by this ket Sz here, we get the same state Sz back again. In this very simple example of a single electron, then we just have up or down spins. We just have a two-dimensional Hilbert space. So this ket can only take one of two values, an up or a down spin. So to describe the spin of a single electron, this is a good basis. How do our spin operators act upon these basis states? If we apply the operator S squared to our basis state, then we get the basis state back again, multiplied by an eigenvalue of 3/4. That is because the eigenvalue of S squared is S into S plus 1, and if we have an S equals a half particle, then here we get this factor of 3/4. Here I am setting h bar equal to 1, that's just a units choice so that the equations don't look so cluttered. Notice here that I get the same equation independently of what value Sz takes. That's because the S squared operator only acts on the spin quantum number, which for electrons is fixed to S equals a half. We also see that this state is an eigenstate of the Sz operator, which returns an eigenvalue of Sz. Notice that here Sz can either be plus or minus a half. This confirms that indeed S and Sz are good quantum numbers, and that we can label our basis states by S and Sz. Furthermore, when we're talking about electrons, we can usually drop the S quantum number because we know that it's S equals a half. Therefore, often it's sufficient just to label the states according to the Sz quantum number. What about the raising and lowering operators? Well, let's act on our state S of a half and Sz is minus a half with the raising operator S plus. In that case, we simply get S equals a half and Sz is equal to plus a half. It raises the Z component of the spin by 1 unit. Similarly, we can apply the lowering operator to the S equals a half, Sz equals plus a half state, and this will give us the S equals a half, Sz equals minus a half state, thereby lowering the Z projection of the spin by 1 unit. Notice in both cases that we don't change the spin of the electron, that remains S equals a half, of course, we just change the Z component. Also, it's important to notice that the Hilbert space is restricted to just these two states. We can see that by applying the raising operator to the state S equals a half, Sz is equal to plus a half. This is already the maximum Sz that the electron can take, so when we try to apply the spin raising operator, we just get 0. Likewise, if I apply the lowering operator to the state with already minimum Sz is minus a half, again, it can't be lowered further, so I just get 0. In terms of our up and down spins, we can summarize this in this nice simple way. Sz acting on up gives us a half of up, Sz acting on down gives us minus a half of down, S plus acting on the down spin gives the up spin, and S minus acting on the up spin gives the down spin. In fact, we can actually express our spin operators in terms of so-called projectors using the Dirac bracket notation. We can write the Sz operator as a half of this projector onto the up state minus this projector onto the down state. The S plus operator takes us from a down to an up, while the S minus operator takes us from an up to a down. Let's look in more detail at why this is the case. For example, suppose that we act on an up state with our Sz operator. According to this definition, we could write that as 1/2 of this object minus this object. But according to the orthogonality and orthonormality condition, this second term here is equal to 0, and this first term is equal to 1. And so overall, this gives us simply a half of the up ket, and that is indeed what we wanted from this first expression here. It's also easy to see that if I'd come along and applied the Sz operator to the downspin, I would have actually picked up this second term. It would have given me minus a half of the downspin, which indeed is correct from here. Let's check out the action of the raising and lowering operators. Imagine that I applied S plus to the downspin. According to the definition, that would be this object. Again, because of the orthonormality condition, this is equal to 1, and so the whole thing is just equal to the upspin, which indeed is the desired operation for acting upon our downspin with our S+. Let's see what happens if we apply our S+ operator to an already upspin. Then I have this object, but again, the orthonormality condition sees that this inner product is equal to 0, and so overall, this is equal to 0. This is correct. It allows us to restrict our Hilbert space purely to this two-dimensional space of up and down spins. All of this is just to set up the formalism for representing a single spin-half degree of freedom. A single free spin-half particle has a special symmetry. It is referred to as SU2 symmetry. This stands for a special unitary group of degree 2. This is the symmetry that describes a free electron. This SU2 symmetry describes the continuous rotational symmetry in three-dimensional space. Now, although we talk about a spin being up or down, this is the Z projection, and of course the Z-axis can be chosen arbitrarily. The actual axis of the spin angular momentum can be pointing along any direction. When we talk about a free particle, we mean that it's not subjected to any potential, and therefore the particle inherits the symmetry of free space, which is isotropic. The spin can freely point in any direction in three-dimensional space, hence the continuous rotational symmetry in 3D space. The spin projection along the arbitrary z-axis can either be up or down. This is analogous to regular angular momentum spinning either clockwise or anticlockwise. To be more precise mathematically, SU2 is the Lie group of 2x2 unitary matrices with determinant 1. This is, of course, no accident or coincidence, because unitary matrices are used for rotations, and the symmetry here is a rotational symmetry. If we have 2x2 matrices, they can describe rotations in three-dimensional space, providing that they are complex matrices. So SU2 is indeed the space of these 2x2 complex unitary matrices. Because SU2 is a non-abelian symmetry, this means that the spin is a non-abelian quantum number. That means that when we combine two spins, it is not simply additive. As you know, when you add S1 and S2 for arbitrary spins S1 and S2, we have the familiar Clebsch-Gordan series. We have different possibilities for the resulting spin of the combined system that range from the absolute value of S1 minus S2 all the way up in integer steps to the absolute value of S1 plus S2. For example, if we have two spin half particles, the combined spin can be either spin 0 or spin 1. By contrast, the spin projection SZ is an abelian quantum number. It means that they are additive. I can obtain the total Z projection of a pair of spins simply by adding up their individual components. We'll talk about how to set up problems involving multiple spin particles in the next lecture. By contrast, however, classical spins are either up or down. There is no continuous rotational symmetry in three-dimensional space, as with the quantum counterpart. A free classical spin has a symmetry between the up state and the down state. It is a discrete symmetry. This kind of symmetry is referred to as a Z2 symmetry, rather than the full SU2 symmetry of a quantum spin-half particle. So let's now consider a simple model, a Hamiltonian, for a free spin-half particle. With full SU2 symmetry, the up and down states must be degenerate, meaning they have the same energy. This is because they are related by a symmetry transformation that's part of the SU2 group. In the first part of the course, we're going to consider spin systems where the electrons are tethered to their lattice sites. We're not going to consider the electrons really moving around. Therefore, we will not talk about the kinetic energy of the particles in this lecture. We're just going to talk about the spin dynamics. The only kind of Hamiltonian we can therefore write down is something like this, something incredibly simple. Here we see the identity operator multiplied by some constant epsilon. If we write out what the identity operator is, we have a projector onto the up state plus a projector onto the down state, and all of that is multiplied by this constant epsilon. So what does this mean? Well, the epsilon here has to be a real parameter describing the energy of the states. It has to be a real parameter because the Hamiltonian must, of course, be Hermitian. We can now use the Schrödinger equation. We apply the Hamiltonian to one of the states of the system. Let's say we apply it to the up spin, and we see that we get the same up spin state back again multiplied by epsilon. So this epsilon is indeed the energy of that state. Similarly, if I act with my Hamiltonian on the down state, then I again generate the down state multiplied by epsilon. So you can see here that the up and down states are both eigenstates of the Hamiltonian, and they have corresponding eigenenergies epsilon. We can also see that we have the same energy for the up state and the down state as required by this SU2 symmetry. Furthermore, we can usually just set this epsilon equal to 0. This is because it is just a constant shift in energies applying to all states of the system and therefore does not affect the dynamics. So this is an extremely boring system. All states of the system have the same energy and there are no dynamics at all. More interesting physics arises when we put the electron into a magnetic field. This provides an external potential and can lift the spin degeneracy. A magnetic field lifts the spin degeneracy. This is called a Zeeman splitting. What kind of Hamiltonian can we write down to describe this effect? Well, the magnetic field couples to the spin of the particle. Therefore, we can write down a Hamiltonian H is equal to minus B dot S. B here is the magnetic field. It's a vector and has components Bx, By, and Bz. However, it is not an operator, it's simply the strength of the magnetic field at this particle's location. On the other hand, S vector hat is a spin-half quantum operator, defined in the usual way. This is the most general kind of coupling we can imagine between a magnetic field and an intrinsic spin of a spin-half particle. Now, at the location of the particle, the magnetic field B is pointing along a particular direction. So without loss of generality, let's call this direction our z direction. In that case, Bz is finite and the other components of the magnetic field will be equal to 0, and therefore when we take the dot product here, the x and y components will drop out. So we can consider the following Hamiltonian. H is equal to minus b is now a scalar quantity, times the z component of the spin, Sz. We can also express this in terms of projectors as minus b over 2 times the projector onto the upspin minus the projector onto the downspin. So unlike the Hamiltonian for a free particle, where we had a plus sign here, we now see that there's a difference between the up and down spins. This is confirmed when we go to the Schrödinger equation. We can use this simple projector formalism here to quickly identify that the Hamiltonian acting on the upspin gives us minus a half b times the upspin back again, whereas the Hamiltonian acting on the downspin gives us plus a half b times the downspin back again. So the up and down states are still eigenstates of the Hamiltonian, but now they have different energy. The degeneracy is lifted, and this is precisely the Zeeman splitting. And the energy splitting between the up and down spins is precisely the field strength B. If we were to plot a diagram showing the energy of these states as a function of the magnetic field strength B, we would see that at B equals 0, both states were degenerate, and then at finite B, the downspin state increases in energy, whereas the upspin state decreases in energy. At any given B, the energy difference between up and down is precisely B. So in a magnetic field, the symmetry between up and down is broken. The symmetry is therefore lowered from SU2 to U1. This U1 symmetry is a unitary Lie group describing the set of complex numbers with absolute value 1. This is a smaller group than that of the SU2 symmetry. The last thing I want to do in this lecture is calculate the magnetization of a single spin-half particle in this magnetic field. This is an extremely simple system consisting of a single spin-half particle. We're just considering here the spin dynamics and nothing else. Yet still, we can find out something interesting when we use the machinery of statistical mechanics to calculate the magnetization. At B equals 0, we have a doubly degenerate ground state. However, at finite magnetic field B, we have a unique ground state. The system becomes spin polarized. Let's now consider an ensemble of spin-half particles, a quantum gas basically, in thermal equilibrium at a temperature T. We can consider the magnetization, which will be simply the expectation value of the Sz operator for our particle, and we could obtain this using the machinery of statistical mechanics. As usual, we can write down the expectation from statistical mechanics in the following way. We write down the expectation value of the operator, sz hat, is 1 upon z, where z is the partition function, and the sum over eigenstates j of this matrix element multiplied by the Boltzmann factor e to the minus ej over kbt. Ej here is the eigenenergy of eigenstate psi j, T is the temperature, and Kb is the Boltzmann constant. In particular, the partition function here, Z, is equal to the sum over all of the Boltzmann weights. This might seem all a little bit complicated, however, here we just have a two-level system, and we know the eigenstates and the eigenenergies exactly, so we can just go ahead and compute this thing. Writing it all out, we get this simple expression. This first term here involves the matrix element of the upspin with the operator sz. This thing is obviously just equal to 1/2. Likewise, on the right-hand side, in the second term, we have a matrix element of the downspin sandwiched between this operator sz. Likewise, this thing is just going to give us the number -1/2. With a little bit of algebraic manipulation, we can actually write this in a simplified and special form as 1/2 of the hyperbolic tangent of b upon 2 kbt. The hyperbolic tangent is arising here because we have something like e to the x minus e to the minus x divided by e to the x plus e to the minus x. So what does the magnetization look like? So if we were to plot the magnetization as a function of the magnetic field strength B, we would see this kind of tangent curve here. In particular, notice that at B equals 0, we must have that the magnetization is equal to 0. That's correct because in that situation we have degenerate up and down spins, neither is favoured, and in an ensemble of particles the average magnetization would be equal to 0. However, as we increase the magnetic field strength, the spin halves become polarized, and the magnetization, the average magnetization, saturates to +1/2 if B is positive, and -1/2 if B is negative. The rate at which the polarization sets in and the magnetization saturates is controlled by the temperature, as we can see from this expression. So, as I've drawn here, for this blue line, let's imagine that this is at a low temperature, whereas in red now, I'm drawing the situation at a higher temperature, where the saturation sets in much more slowly over a wider range of B. By contrast, at T equals 0, at absolute 0 temperature, we would see that this becomes very sharp indeed and tends to a step function. Okay, so even though this is an extremely simple system, we still find some interesting physics here. In the next lectures, we'll be considering how to generalize this to multiple particles. In this lecture, we just talked about a single spin-half particle. How do we generalize this to 2 particles and more particles? In the end, we're going to want to discuss the spin dynamics in real materials, which have 10 to the 23 particles. How do we take that big leap? For the answer, check out the next lecture.